Hi. In this video, we are going to basically recap what we have learned in the past two classes and all the techniques that we have learned. We'll just apply it to a few problems and see if we are able to use those techniques properly. So as mentioned before, when we discuss a problem, please try to do it yourself without watching the video. You can pause the video and try it yourself before you look at the solution. We'll start off with this one, question number 1. This says let f of x be equal to root over 20x square plus 10. You have to find the formula for f of n of x, where basically the notation here means this is f n times of x. So you're doing composition and n times. So as before, we had learned in the previous video the fixed point method, so we can apply that here. So first thing we will see is what is the fixed point of this function. F of x is equal to x. So this tells us the fixed point. So we'll say root of 20x square plus 10 is equal to x. If you square it, you'll get 20x square plus 10 is equal to x square. And you get 19x square is equal to minus 10. So x square is equal to minus 10 by 19. So basically you realize that the fixed point is a complex number here, right? So it's not a real number, okay? So 20x square plus 10 can be basically rewritten as 20 times x square minus 10 by 19. So they basically think about it. You have to subtract then minus 10 by 19, right? Because technically what we did earlier when we had ax plus b was ax minus b by 1 minus a plus b by 1 minus a. This b by 1 minus a was the fixed point of this function. We are trying to do the same thing here. You can confirm this, you can multiply it out and realize that this is 200 by 19 minus 10 by 19, which is going to be basically 190 by 19. So that becomes what? That becomes 10, right? So it is actually matching. 20x square plus 10 is equal to this, right? So therefore, the function f of x can be written as root over 20 x square minus 10 by 19 minus 10 by 19, and which is basically root over 20 x square plus 10 by 19 minus 10 by 19. Now this is my function f of x. So let's see whether the patterns that we saw earlier for fixed points still work. We'll try to find f of x and see what happens. So f of x would be basically root over 20 and f of x square plus 10 by 19 minus 10 by 19. Because we know that f of x was root over 20 x square plus 10 by 19 minus 10 by 19, right? So if you evaluate this becomes 20. F of x square is what? F of x square is 20 times x square plus 10 by 19 minus 10 by 19. And you have a plus 10 by 19 inside and then a minus 10 by 19 here, right? So if you see what happens here, this becomes 20 square into x square plus 10 by 19 minus 10 by 19. So can you see that the pattern that we wanted is happening again? F of 2 of x is basically 20 square and the form here is the same that was there, the form here. So by induction, you can show now that f of n of x should be equal to root over 20 power n x square plus 10 by 19 minus 10 by 19. So this is our answer. This is the function that we are looking for, is the composition of f n times. So that's just a quick recap for your fixed point method that we saw in the previous discussion, right? Previous video. Next question is this one. Question 2. You have to find a function g of x. Find a function g of x such that g of 8 of x is equal to x square plus 2x. G of 8 of x is equal to x square plus 2x. Now, this this function is clearly x plus 1 whole square minus 1 by the way, g of 8 of x, right? So what I want to do is I want to use the bridge function method here. The bridge function method said that we have to find two new functions. One is the bridge function and one is the third function. We have to say that the g is similar to f through a bridge function phi, right? So we will say we have, let's say g of x is equal to x square plus 2x, and phi of x, let's call that as x plus 1, and the third function h of x is x squared. Now, how do I know that these functions will work? I'm just checking this condition. I'm saying basically phi of h of x is equal to g of phi of x, right? So basically we can see phi of h of x is what? H of x plus 1, and that comes out to be x squared plus 1, and g of phi of x is what? G of x plus 1, right? G of x plus 1 will be yeah, I think I've made some mistake here. Let's see. This becomes, if phi of x is x plus 1, you have phi inverse of x is x minus 1, right? Phi inverse of x is this, and we have to check phi inverse of h of phi of x. That should be g of x, right? Correct. So h of phi of x is what? H of phi of x is phi of x square. So that is x plus 1 whole square, right? Correct. And phi inverse of that would be basically x plus 1 whole square minus 1, and that is equal to x square plus 2x, which is equal to g of x. If now we have confirmed, basically we had to check phi of g of x should be equal to h of phi of x. This was the condition. Then we can say that h and g are similar with a bridge function phi, right? So once we have established that, right, we know from previous theory, if g of x was equal to phi inverse h of phi of x, then g of n of x comes out to be g of n of x comes out to be phi inverse of h of n of phi of x, right? So this was the theory that we had developed in the previous video. G of n of x is equal to phi inverse of h of n phi of x, right? So now what we will take is, if we let u as x power 2 power 1 by 8, because remember we have to get g of 8 of x is this, right? So we will define a new function u of x is x power 2 power 1 by 8, okay? Then you can say that h of x is equal to h of x is equal to x square can be written as u of 8 of x, right? Can you think about this? Calculate u of 2 of x, or basically u of x. You will realize that that will be x power 2 power 2 by 8. And u of 3 of x would be x power 2 power 3 by 8. So finally, u of 8 of x should be x power 2 power 8 by 8, which is x power 2, right? So h of x is equal to u of 8 of x, right? Here. You can confirm that yourself. H of x, which is x square, is the function u composed with itself 8 times, right? Great. So now, therefore, we have here by this result g of 8 of x should be equal to phi inverse of h of 8 of phi of x, right? Correct. But actually we should not take h, we should take u. U of 8 of phi of x, right? So this happens if and only if we can define, if we say that g of x is equal to phi inverse of u of phi of x, then g of 8 of x will be equal to phi inverse of u power 8 of phi of x, right? Now u of 8 will become an h of phi of x inside, right? And h of phi of x is phi of x square, right? H of phi of x is just phi of x square. So we know that this result is true. So phi inverse of h of phi of x is simply gx, right? Correct. So g of 8 of x is coming out to be that is matching, right? So what we get now is our g of x is equal to phi inverse of u power 8 will become u of 8 of phi of x is x plus 1, and u of 8 of x plus 1 will basically start looking like x plus 1 to the power 2 power 1 by 8, right? G of x will start looking like phi inverse of x plus 1 to the power 2 power 1 by 8, right? And that basically looks like pi inverse of that is x plus 1 to the power 2 power 1 by 8 minus 1. So I'll do that in the next screen properly. Like right now it is a little confusing. So what we are saying is that the original function f of x was x square plus 2x, right? And not f of x, let's call that g of x. G of x was x square plus 2x. Now we have to say that this is actually g of 8 of x, right? So let's call it f for that reason, because then we'll say the f of x is equal to g of 8 of x, right? So if I take my phi of x as x plus 1, I get phi inverse x as x minus 1, and I'm going to take h of x as x square, and I'm going to take a u of x as x power 2 power 1 by 8, where we can see clearly that u of 8 of x is equal to h of x. We have this result, right? So we can say that f of x and h of x are similar through phi of x. Why? Because we can verify that phi of f of x is equal to h of phi of x. What is phi of f of x? Phi of f of x is f of x plus 1, and h of phi of x is phi of x whole square, right? And f of x plus 1 is x square plus 2x plus 1, and this is x plus 1 whole square. So you can see that these things are matching. So our statement is correct. F of x and h of x are similar through phi of x, right? Phi of x is our bridge function for f and h, right? Okay. So therefore, f of x is equal to phi inverse of h of phi of x. We have this result, right? Now, if because we have u of 8 of x is equal to h of x, right? Hence, if our g function g of x is defined as phi inverse of u of phi of x, right? That would mean that g and u are similar also through phi of x. Through phi of x. We have to find out g. G is unknown for us, right? U we have taken as x power 2 power 1 by 8 because this to compose 8 times becomes h, right? So if g and u are similar through phi of x, then we can say that g of 8 of x should be equal to phi inverse of u of 8 of phi of x, right? And now, because we know that u of 8 of x is h of x, this can be written as phi inverse of h of phi of x, right? Phi inverse of h of phi of x. And phi inverse of h of phi of x is f of x, if you can see here. So this is f of x, right? So that means f of x is x square plus 2x, right? And g of 8 of x is becoming equal to x square plus 2x. So therefore, g of x must be equal to simply phi inverse of u of phi of x, right? We are getting the initial condition that we wanted. G of 8 of x should be equal to f of x. So this relation is confirmed. So we'll say that g of x then must be equal to this, right? If g of x is equal to this, then what we get g of x is equal to basically u of phi of x. So u of phi of x would be phi of x to the power 2 power 1 by 8, right? And you have to do a phi inverse outside. Now phi of x is what? Phi of x is x plus 1, right? So it is x plus 1 to the power 2 power 1 by 8, and phi inverse x is this minus 1. So that should be my g of x. Okay? Hopefully now it is clearer. I was just trying to get a handle on the functions in the previous screen. It should be clear now. You are basically doing the reverse operation. We are not trying to find the composition. We have the composition. We have to go to the base step, right? Okay. The next question for us is this one. Find all functions. Find all functions f from n to n such that for all xy belongs to natural number, we have f of x plus f of y is equal to f of x plus y. Notice one pattern here. Here x and f of y was the input. And now we have output is f of x plus y. So they got interchanged, right? This is our first result. We have to find all possible natural number functions, right? So natural numbers to natural numbers. So the first step is we take let f of 1 is equal to a. We don't know the value of a. And now we put x is equal to y is equal to 1 in the first equation. This is my first equation in 1, right? If you do that, you will get f of 1 plus f of 1 is equal to f of 1 plus 1, right? So that means this can be written as f of 1 plus a is equal to 1 plus a. This becomes our second result. There will be many results in this question, so keep track of them basically. Because we are using f of 1 is equal to a, we have said let f of 1 be equal to a. We are using that to get the second result, right? Now, the next step is putting x and y as equal to 1 and 1 plus a. So we'll get f of 1 plus f of 1 plus a is equal to f of 1 plus 1 plus a, right? So this becomes equal to f of 1 plus a, we will use the second result as 1 plus a. We'll say f of 2 plus a is equal to, and this becomes f of 1 is a, so this becomes 2a plus 1, right? This becomes our third result. F of a plus 2 is 2a plus 1. Now, f of 2 plus a can be written as f of 2 plus f of a is f of 1. So using the first property here, f of 2 plus f of 1 will be same as f of 2 plus 1. Here x is 2 and y is 1, so output will be f of x plus y, right? So we are getting f of 2 plus a is equal to f of 2 plus 1, right? Now f of 2 plus a we already know is 2a plus 1 from 3. So 2a plus 1 is equal to f of 2 plus 1, which implies f of 2 is equal to 2a, right? F of 2 is coming out to be 2a. This is the fourth result. So notice we are getting a lot of data here. We are getting f of 1, let f of 1 is a, and from there we have found f of 1 plus a, f of 2 plus a. We have now found f of 2, right? So let's go to the next screen and keep these information in mind, and we'll be using that again. So now we'll say what is f of 1 plus 2a, right? 1 plus 2a is basically equal to f of 1 plus f of 2, because we just now proved that f of 2 was equal to 2a, right? And now using the first identity again, this will be equal to f of 1 plus 2, right? So that is equal to a plus 2. And f of 1 plus 2a is now coming as a plus 2. Again, doing this in a slightly different way, f of 1 plus 2a can also be written as f of a plus 1. And we already know that f of 1 plus a is equal to 1 plus a. This was our second result, if you recall. So this is equal to f of a plus f of 1 plus a, and which will be written now as f of a plus 1 plus a, right? Using the first equation 1 basically. Now we are getting f of a plus 1 is also equal to this. So both the things must be equal. Therefore, we can write a plus 2 should be equal to f of a plus 1, right? Which implies that f of a is equal to 1. This is a very important step. We have proved that f of a is 1, right? We have already assumed that f of 1 is a, right? F of 1 is a and f of a is 1. Both of the things we have got, right? Now we can say that f of 2a is equal to f of a plus a, which is equal to f of a plus f of 1, which is equal to f of a plus 1, right? And now f of a is 1, therefore this is 2, right? So therefore we are getting f of 2a is equal to 2, right? And also, so we can also write this as f of 1 plus 2a minus 1 is equal to f of 2a minus 1 plus 1 can be written as f of a using this result. And this can be now written as f of 2a minus 1 plus a, right? So that should also be 2, right? Because this is f of 2a only. F of 2a is equal to this. So this should also be 2. So therefore, we are getting a plus f of 2a minus 1 is equal to 2. We are getting this result, right? This is the key step, the last step here, because we know that, okay, I'll do it on the next screen. We know that a plus f of 2a minus 1 is 2. We have gotten this. And we know that f was from naturals to naturals. The output of f has to be a natural number. And the input also is a natural number. So this is also natural. 2a minus 1 is a natural number, first of all, belongs to a natural number. And also f of 2a minus 1 is a natural number, right? And we know that a is also a natural number, right? Because a was the value of f of 1. A was equal to f of 1, right? So that means sum of two natural numbers is 2. So that means a must be 1, right? Because otherwise this will be 0. But the output of this cannot be 0, right? And a also cannot be 0 because the domain and codomain are natural numbers. So this equation itself implies that a is equal to 1. And if a is equal to 1, we have f of 1 is equal to 1. And all the data that we have found, we can now show that f of x plus 1 is equal to f of x plus f of 1 is equal to f of x plus 1. And therefore, f of x plus 1 is coming as f of x plus 1. By induction, now we can show that f of 2 is 2 and f of 3 is 3. And therefore, you can by induction very easily prove that f of x is x. So f of x is equal to x is the only solution for this functional equation. And we got it because we derived this condition. And we derived this condition after a lot of tricky steps. Not very tricky, but a lot of steps where we took different values of x and y and kept getting new equations, right? Okay. The next problem that we look at is this one. Find all non-zero functions. Find all non-zero functions f from R to R such that for all real numbers x and y, for all real numbers x and y, we have f of x multiplied by f of y is equal to f of x minus y. F of x multiplied by f of y is equal to f of x minus y. Now, the first step here is we put x is equal to y. If you do that, you will get f of x whole square is equal to f of 0. Right? Now, this equation is true for all real x, according to the statement of the problem. So, if I put x is equal to 0, that implies f of 0 whole square is equal to f of 0, right? So, that basically means that f of 0 is equal to 0 or 1, right? Now, if f of 0 was 0, what would happen? In this condition, you would say that f of x whole square was 0 for all real x. But that will make f of x equal to 0 the only solution, right? And that will make f of x a 0 function. It's not a non-zero function because all the outputs will be 0 only. So we will basically reject this case. If you take the case that f of 0 is 0, you get a 0 function. The function is a constant function which is 0. But we want to search for non-zero functions. So therefore, we will say that f of 0 is equal to 1, right? And if f of 0 is equal to 1, that implies that f of x whole square is equal to 1, which implies that f of x can belong to, it will be either 1 or minus 1, right? F of x is going to be either 1 or minus 1 for every x, right? Now, how do we find whether it is 1 or minus 1? Very simple. We'll say y is equal to x by 2 here in this original equation. You will get f of x into f of x by 2 is equal to f of x by 2. And we'll be able to take it on one side and say f of x minus 1 multiplied by f of x by 2 is equal to 0. But we know that the functions are non-zero. So f of x by 2 is not equal to 0, which implies that f of x is equal to 1. So the only solution, only function that satisfies this functional equation is f of x equal to 1, right? So that's this problem. Now, we have sort of concluded the functional equations part of the syllabus. We will come back to functional equations later with some more problems, but at a slightly more advanced level. Right now, I hope that these videos, these 3 videos and the problems therein will help you attempt questions in a better way and give you a little bit of a leg up as compared to your competitors. Hopefully, you have learned something from these videos, and I'll see you next time.